Let's start. It's my big pleasure to introduce Xavier Roulleau from France, who will speak about on the geometry of K3 surfaces with finite automorphism group.
Well, thank you very much. Thank you very much for the invitation. Very glad, and thank you for coming to my talk. So yes, I will speak about K3 surfaces with a finite automorphism group. So this is part of this talk is a joint work with Michela Artebani and Claudia Correra Diasler. So let's start with the notations. So X will be a complex projective K3 surface. So I recall, so it is the surface, and I recall that K3 means that the canonical bundle is trivial and the H1 is also trivial. So examples are well known: double cover branched over sextic curve in P2, quartics in P3, degree 6 complete intersection in P4, and so on. So NS of X will be the Néron-Severi group of the surface X, and the rank of the Néron-Severi group is usually called the Picard number of X. And we have the well-known bound for the Picard number, which is between 1 and 20, 1 because the K3 is projective, and 20 because the upper bound is H11. A smooth rational curve on the K3 is called -2 curve. It comes from the adjunction formula. So the square of smooth rational curve is -2. And yes, be careful in that talk. I will often confuse a -2 curve and with its class in the Néron-Severi group. It's not the same, but it's convenient to have that shortcut. And finally, I denote the linear equivalence between divisors by this equivalence relation. So let me recall a bit on the history of the Nikulin-Weinberg classification. You all know that a smooth curve has a finite automorphism group if only if the genus is 1, is bigger than 1, strictly. For K3 surfaces, there is analogous classification that started from the Italian algebraic geometry school. You can think to the Cremonia group for the plane versus the surfaces of general type, which have a finite number of automorphisms. And in the 70s and early 80s, the K3 surfaces with finite automorphism group has been classified by Pietetsky, Shapiro, and Shafarevich. In fact, that was a corollary of the Torelli theorem. So for the case of Picard number 1 and 2, then Nikulin and Weinberg made the other cases. So Weinberg for the rank 4 and Nikulin for all the other ranks. And so that talk will be concentrated on Nikulin and Weinberg classification, so for the Picard number larger than 2. And the K3 surfaces with finite automorphism group and Picard number larger than 2. So the output of the Nikulin-Weinberg classification is a long list of 118 families of such K3 surfaces. So each family, so I denote the modulus of these families, ML, where L is a characterization of L is the lattice, which is isomorphic to the Néron-Severi group. So the 118 families, the output is 118 lattices, which are Néron-Severi group of K3 surfaces with finite automorphism. Okay, and yeah, a remark on the dimension of the moduli space of this K3, it is 20 minus the rank of the lattice. yes, I will need more notations. So we are speaking about lattices. So ADE are the negative definite lattices associated to a root system with the same symbol. And I will, when there is a symmetric integral matrix M, I denote by bracket M the lattice with a ground matrix M. For example, the lattice of the hyperbolic plane is 0, 1, 1, 0. And yeah, a last notation that L bracket M means the lattice L with a quadratic form multiplied by M. It's all classical notations. And so a few examples of the lattices among the 118. So these are the lattices of Néron-Sévry groups of K3 surfaces with finite automorphism. So here are a few examples. So the first has rank 3, and there are rank 4, 4, 5, 9, 11, and 19. And so if we have time, we will study these examples more accurately, not the last one. The last one is here because so it has rank 19, and this is the largest rank for a Néron-Sévry group of K3 with finite automorphism. So, but let me motivate a bit more this K3 with a finite automorphism group. So another point of view is that a surface has a K3 surface has finite automorphism group if and only if that K3 has a finite non-zero number of -2 curve when the Picard number is larger than 2. So it is a very nice characterization, and it is interesting. Yeah, the -2 curves play a key role in the geometry of K3 surfaces, and you can see it by that nice result of inequality. Another viewpoint is that is the one of a Cox ring. So the Cox ring of the variety is the direct sum over all the classes of the space of section of the divisors. So it is a ring. And for which, so Artebani, Hausen, Laface, and independently McKernan proved that a K3 with a Picard number larger than 2 has a Cox ring finitely generated. So this is also called Mori-Dream surface. If and only if the effective cone is polyhedral, which means that there are a finite number, non-zero number of -2 curves. So the number of -2 curves, yeah, the number of -2 curves is bounded above, as we will see. So there is only 118 families, and each family has the same number of -2 curves, which is finite. Yes, a last point of view, which is interesting for these surfaces, it is the nice result of many people. So there is the list here, that K3 surface contains infinitely many rational curves, which means rational curves is here surface of geometric genus 0, so maybe singular. And the most difficult case that remained were K3 surfaces with finite automorphism group and Picard number 4 and no elliptic fluctuation. So I will speak about one example of this kind of surfaces which were difficult for the theorem I just quoted. Okay, so what are my aims? So it is to go from abstract lattices, so the characterization, the 118 families are 118 lattices. So these are not very much surfaces, but the Torelli theorem tells us that this is a very good characterization for these surfaces. But I wanted to see these surfaces more alive. And for me, what means alive is by equation, and one can construct. I want to construct these surfaces. So we start from a lattice of the Nikulin-Weinberg classification, and I want to describe the finite set of -2 curves on the K3 surfaces which have that Néron-Severi group. So that knowing these -2 curves means for me knowing the intersections or the dual graph of these matrices of these curves. So I want to obtain a geometric model of these surfaces as a double cover of some known surfaces or surfaces in a projective space, and describe so the equations and the realization of the -2 curves as line, conics, or higher degree curves in a projective space. And then I want to study the unirationality of the moduli spaces, of the various moduli spaces, ML of these surfaces. So what I did for each of the 118 lattices, so the first 2 points are done, and the third point I obtain at least 60 of these moduli space are unirational. So let me give you the plane of the remaining of the talk. So this is not very much a plane, it is a journey through the world of K3 surfaces. So I am dealing with 118 examples. So I will start with explaining the tools I used. I will give a first series of 3 examples. I will make a remark on there is a connection, a link with the famous 95 families of K3 surfaces constructed by Ride. And from that, one obtains an unirationality of many K3 surfaces with finite automorphism group. I will also speak about Nikulin star-shaped lattices and K3 surfaces. So Nikulin was able to characterize some kind of K3 surfaces with finite automorphism group and the configuration of their -2 curves. I will give you a table with the results, and if I have time, I will speak about more involved examples. So I wanted to start with a tool that I call the sieve of Eratosthenes-Weinberg for the K3s. So I will explain you why I call that that way. So we start with so the place to start with a lattice of the Yoka K3. It is the only thing you know at the beginning, and you want to construct all the -2 curves on your K3. So you start by choosing an ample class as an element which has a square, positive square, and orthogonal complements do not contain roots. So it means a root. A root for me. A a root for me is a curve, a class with a square equal to -2. For any integer d, you can define the set of degree less or equal than d roots. So it is that set rd plus like positive. So it is the set of classes in the lattice which have that. So the degree is that P intersected with C, and so the P intersected with C is less than D and bigger than 0, and you want the class which has square equal to -2. So by Riemann-Roch theorem, root is the class of an effective divisor on X, and you can define, now you have the roots, and you want to understand which of these roots are primes, which means for me irreducible classes of -2 curve. You want to know which one are classes of -2 curves. So you can, for that, you start with the first D0, such that the set Rd of roots of degree less or equal than D is not the empty set. And if you have you find easily if if a class is not irreducible, then you can suppose that it splits as a sum of two curves, and one of these curves has c square equal -2, but then that curve would have a degree less than d0, which is a contradiction. So the thing you have to see. So we see that the set of nd is the set of nd0 is simply the set of roots of degree less or equal than d0. So this is an induction process, and this is the first step of the induction, the initializing step of the induction. Okay, so in that slide, I repeat the first four lines are copy paste of the four last line in the previous slide. So now you suppose that you know the set of -2 curve up to degree d. So that set is nd, and you take a root of degree d+1, and you suppose that for every root, every nodal class, classes of -2 curve, the intersection of your root C is positive or 0. And you suppose, moreover, that C is not irreducible. Then you have that your C is split as a sum, and with the component Ci, so effective of degree less than d-1, and the Ci are all positive, or Ci are classes have a positive square, or are classes in the nodal class are -2 curves of degree less or equal than d. But then when you compute the self-intersection number of C, you get that you compute it in two ways. You know that the self-intersection is -2, but with this formula, you get that the self-intersection is positive. So the absurdity was to suppose the supposition here was the end here. And thus you may conclude that the set of -2 curve of degree d+1 is that set. So it is the set of degree, well, it is less or equal than d+1. It is the set of -2 curve of degree d union that set of roots which have degree d+1 with respect to the polarization p, and such that for every curve of degree less or equal than d, the intersection is positive or 0. And so, yeah, the algorithm for finding the -2 curves among the -2 classes is like the sieve of Eratosthenes. If you know the primes of degree less or equal than d, then every root of degree d+1, such that the intersection with C is negative, must be discarded, and the remaining roots of the d+1 are primes, which means for me -2 curves. So instead of a division algorithm, the thing that replaced the division algorithm is the intersection number, which is negative. So it's a nice algorithm of Weinberg. Of course, he didn't use that languages of K3 surfaces. So he passed away this month, and I wanted to put a picture of him. There is a nice interview in the EMS newsletter in December 2000. December. Yes, let me continue about the tools. So the effective cone on a K3 with finite automorphism group is a polyhedral. So it is the cone generated by the -2 curves. And the dual cone is also the polyhedral. This is the NF cone. And now there is, so using Weinberg results, you got that you got -2 curves, but in order to control that you have all -2 curves, you have to use characterization by Weinberg, and well, also Artebani, Correa, Diessler, and Laface for the formulation, at least with the K3 surfaces. So if you have -2 curves, you take the effective cone, the polyhedral cone generated by this curve is the effective cone, if only if the facets of the cone are semi-definite negative. And then once you know the NF cone, you can have an interesting example of NF or ample classes. And we use these classes to obtain interesting projective models of our surfaces. I will, so I will call the last classical tool I will use is double cover on -2 curves. So if you have a K3 surface and a base point-free linear system, so you have a base point-free linear system, D2 with D2 square equal -2. So it corresponds to a double cover, which is branched over a plane elliptic curve. So that double cover constructs the -2 curves A, which such that the intersection with D2 is 0, and that contracted to ADE singularities of the curve C6. If you suppose that your divisor is linearly equivalent to two -2 curves A1, A2, such that you have that, the conclusion is that there is a line such that your divisor D2 is linearly equivalent to the pullback of the line, and the line is tritangent to the branch locus. So we have the line, branch locus, and we have that picture, sorry. And over that, so you have the branch locus, and the line splits. So picture should be like that. And like that. So this is the ramification locus, A1, A2, and here line and the branch locus. Why that? It is because the tangency condition here make no ramification at that point, and if you have no ramification at the 3 points, that means that your no ramification of rational curves is you have 2 curves on the pullback. Okay, let me now go to the examples. Well, sorry, I want to go too fast. So, and there is the same result. So it is the second part of the proposition. If you have your 2D2 linearly equivalent to 2 minus 2 curves, such that the intersection number is 2, then that means that in fact your curve, there exists a conic on the plane such that the A1 plus A2 is the pullback of the conic, and the conic is tangent at every intersection point of the branch locus. It's very classical. So let me start with the first example. So the case S611. So using Weinberg algorithm, you compute that there are 4 minus 2 curves on that surface with intersection matrix, that matrix. Yeah, the blue, there is a 2 in blue, because we will need it for further explanation on the next slide. So the curves, the first 3 curves generate the Néron-Severi group, and you have that D4, the sum of the 2 first minus 2 curves square 4, and the sum of the 2 last minus 2 curve is twice linearly equivalent to twice D4. So I put equal, but it is linearly equivalent. And the conclusion is that then the surface is a quartic in P3 with a hyperplane section, which is union of 2 conics, on the quadric section, which is the union of 2 degree 4 smooth rational curves. And second part of the position, that the moduli space of these K3 surfaces is unirational. Okay, so for the proof, so you compute that in fact your divisor D4 is ample because the intersection with all the minus 2 curve is positive. You have D, AG positive for all minus 2 curves, and that gives you that it is sufficient to verify that the ampleness with these curves. And for the very ampleness, you use some easy criteria of Saint-Donat. So that gives you that your surface is a quartic in P3. And moreover, since you know that D4 is linearly equivalent to that and that, the image of A1 and A2 are conics through the embedding given by D4, and the images of A3 and A4 through the embedding are 2 smooth rational degree 4 curves. So now for the second part, in fact, it is more than that. It is the second part gives you a construction of these surfaces. So you start with a conic C1 and a smooth rational curve C3, and you ask that your conic on the degree 4 rational curves cuts into a degree 2 scheme, the intersection of these 2 curves, and then you take you take your generic quartic that contains this conic and the degree 4 rational curve. Now you consider the plane that contains the conic, and so there is a residual conic, and so that gives you a second conic contained in your K3 surface Q4. And moreover, so in fact, it is an exercise in the book of Hartshorne that one can prove that there is a unique quadric Q2 that contains C3. And so when you take the intersection of your surface Q4 with the quadric Q2, it contains the curve C3. Sorry, it is a 2. Yeah. It contains the curve C3, so there is a residual curve which has degree 4, and that residual curve is C4. And then you compute the other intersection number, and well, you get that the intersection number of C3 and C4 is 10, and everything is like is here. So the intersection number of the curves C1, C2, C3, C4 are the same as the intersection number of that matrix here. So thus to construct the surface we wanted, so it is the same as constructing the curve C1, C2 with that intersection number, and then you take a quartic, generic quartic in the linear system that contains them, and you have your surface. And so everything in that construction is parameterized by rational parameters. So the moduli space is unirational. The second example, so it is in fact 2 examples in one. So it is one construction for 2 lattices. So there is a kind of twin phenomena. So I will consider X and X prime, 2 K3s with Néron-Severi group L12 and L24. So these are notations. So you see these are rank 4 lattices. Lattices of which are Néron-Severi group of K3 surfaces. And the proposition is that there are exactly 6 minus 2 curves on X and X prime, and you can label these curves such that their intersection matrices are these 2 matrices. So it's a bit difficult to see what are the differences in these lattices, but so the differences are here. You see that the 1 and 0 are exchanged. Yeah, so there is very little differences between these 2 intersection matrices, and both K3 surfaces have a finite number of minus 2 curves, so which is 6, and yeah. So let me continue on the properties of that K3. So you take the 6 minus 2 curve to be A1 up to A6 on X, and I take the same notation for X prime because they have the same property. We can write the proposition like that. So the divisor D2, which is sum of A1 plus A2, is ample of square 2, and you have the linear equivalence, D2 linearly equivalent to A3 plus A4, and also to A5 plus A6. So that gives you that the linear system so it is base point free. It gives you a double cover of the plane bunched over a smooth sextic curve. And the three curves are mapped onto three lines in P3, P2, which are tritangent to C by what I recorded previously. And if you do the converse, if you take Y, the double cover of P2 branched over a smooth sextic curve, which has three tangent lines, and you suppose that the Picard number is 4, then either the neurosilvery group is L12 or L24. So the two cases. So recall that for X, the neurosilvery group is L12, and you can find the equation of the branch locus of the double cover. So you find that this branch locus is this one, where the Li are modular form and the F and G are cubic forms. In fact, the Lg equals 0. These are the equation of the three lines here in P2. From that, so these lines, so finding a surface with neurosilvery group L12 is the same as having such an equation, and this is a rational parameterization, so you conclude that your moduli space is unirrational. Now, what about the other case, which is L24? So it is. So I can give an example. I take linear forms L1, L2, quartic form, and a cubic, and I look to the smooth sextic, and you can find that it has three tangent lines, which are the lines L1 equals 0, L2 equals 0, and the third line is Y equals 0. When you do Y, the double cover branched over this C6, you find that the pullback of the lines create -2 curves and generate a neurosilvery lattice, which is L24. And now you use Weierstrass conjectures and reduction modulo 13, count the point and articulate formula so that you obtain that the Picard number is 4, and well, you conclude that your neurosilvery group is L24. There is no overlattice in the neurosilvery group, moreover, containing L24. So that example, I have not the general construction for these K3 surfaces. So a remark is that these surfaces are more difficult to construct because they have no elliptic fibration. At the opposite for X, for which NS of X is L12. So it is the first remark. The other remark is that the automorphism group is Z over 2Z. It is the automorphism of the double cover. It is so this is a result by Kondo. So let me give a third example. So it is an example with a lot of -2 curves. So Kondo has proved that for this surface, so it is the surface with neurosilvery group U2 plus A1 to the 7. So it is the, well, first part is 2 times the hyperbolic plane, and the other the other place, -2 on the diagonal. So Kondo has proved that the automorphism group is Z over 2Z to the square, and it is generated by non-symplectic convolution, sigma 1 and sigma 2. So from that, one can construct these surfaces in 2 ways. And the second is, so the first one is very natural, it's obvious, and the other one is an unexpected construction. So the quotient surface by the first non-symplectic convolution, it is a del Peso surface of degree 1, and the quotient map is a branch of a smooth genus 2 curve. And there is a blowdown map such that the image of C, so the branch map is the image of the branch map is a sextic curve with 8 nodes. At each of the 8 are contracted -2 curves. So conversely, if you start with a plane static which has 8 nodes in general position, then you take the minimal desingularization of the double cover is a K3 surface with non-Silveri group U2 plus A1 to the 7. And the K3 surface contains 240 -2 curve exactly. And these are the pullback of the 240 -1 curve on the Del Pezzo degree 1 surface. Now the second construction. So on a degree, so you have on your Del Pezzo degree 1 surface, you have kz square equal -1. Now if you take, so that means that f1 square of kz equal 2. So if you take the pullback by f1 of the pencil minus kz, that gives you a double cover, another double cover, and which is the double cover associated to the second evolution. And that times the bunch locus is a smooth sextic curve to which the 120 are tangent at every intersection points. And the 120 conics are the image of the 240 -2 curves on your surface, on your K3 surface X. So now I will mention 2 general results. So, so the first one is about a work of Hyde and Yonemura, which classified K3 surfaces, which are anti-canonical divisor with at most Gorenstein singularities in a weighted projective threefold. So these families, 95 families, are called famous 95, and these families are classified according to the possible weights of the weighted projective spaces. And moreover, Belcastro has studied the Néron-Silv group of these surfaces and the Néron-Silv group of the mirror. There is a mirror symmetry theory, and she computed that. And so we do two remarks that the 95 famous moduli spaces are unirational. So you just have to check that the surfaces, the linear system, the anti-canonical linear system on this weighted projective threefolds contains all the K3 surfaces of the family. And this is interesting because among the 95 families, 25 are K3 surfaces with finite automorphism group. So you obtained in that way for free that 25 of your moduli spaces of K3 with finite automorphism group, that these families are unirational. And yeah, another remark is that among the mirror surfaces, 7 families are K3 with finite automorphism group, which are not listed among the 95. Okay. And the second work I wanted to mention, the second point I wanted, general result I wanted to mention is the result of Nikulin. So with another point of view, which is rather a corollary of the work of Nikulin. So the result is that Nikulin gives the number of -2 curve and their configuration for some of the K3 surfaces we are studying. So when you have a K3 surface with an Héron-Sevry group which splits as some direct sum of U, so it is the hyperbolic space and hyperbolic lattice of rank 2, so 1, 1, 0, plus K, where K is negative definite. It's not written, but it is negative definite. So there is a conclusion, well-known conclusion, that there is an elliptic pencil with a section, and a fiber on the section generates a lattice isomorphic to the hyperbolic lattice U. And now if you suppose that your K here is a direct sum of lattices ADE, then the fibers that are non-irreducible of the fibration are of Codera numeration. You know all the non-irreducible fiber of your fibration by taking the extended dating diagram of your fibration, of your lattice here. So it is better to give an example. Well, so first, the dual graph formed by the -2 curve on the singular fiber, non-irreducible singular fiber. It is rather irreducible. And by the section of the fibration is called the star of the lattice. So it is a graph of that. So a better example is it is better to give an example. So here you have the section so you have that lattice. I gave you the section. You have A2, the extended diagram of A2 is A2 tilde here, and 2A1, so first A1, first A2, and so that means here that this is the dual graph, so the curves, the singular fiber is like that here, and for the two it is like that or like that. Here there is a tangent. So what you do is that if your K3 is U plus K and K is like that with G, A, D, E, then you can associate the star of your lattice. Formally, it is a graph. And the conclusion of Nikulin is that if you have a K3 surface with Néron-Sevry group isomorphic to U plus K, where K is among the 29 lattices, then you have a finite automorphism group, and the star of the lattice is the dual graph of all of the -2 curve on X. And moreover, well, you can construct these K3 surfaces because you know, and you can know precisely where are the -2 curves because you can search, for example, a Weierstrass model of the natural fibration. Yeah, I must mention also that Nikulin gave also the number and configuration of -2 curve for some other case, in particular when the picker number is 3. So I will show you now a classification table. So let me explain the notation. This table, the main aim of this table is to give the number of -2 curves on the 118 families. But for some of these families, the computation made by a computer never stops. So I put a thing dagger on the side when it is only a lower bound that I know. An Aleph means that the lattice is among the 95 families. An angle, it is a mirror of one of the 95. A star, that the configuration is as predicted by Nikulin. And U means you have the irrationality of the moduli space. well, unirationality means in practice that you know to construct all the surfaces in the family. So let me show you that classification. Okay. So we start with a rank 3. There are 26 examples in rank 3. And so we know I searched to understand the unirationality questions only systematically only for rank 3 and 4. And you see that a lot of these moduli spaces are unirational. So yes, let me, so you see here, and so the rank is given here. The number of -2 curves are this in those column. So so the rank 3 are these 26 cases here, and most of them are unirational moduli spaces. So rank 4, there is a lot of cases, 5, 6. So in rank 3 and 4, there is not a lot of -2 curves. The maximum of -2 curves is 12 here, and the lower bound is 3. But for higher rank, so here rank 5, if we have time, we will see an example with 24 -2 curves, and their configuration is very nice. And when the rank increases, you have more and more -2 curves. For example, in rank 7, you have 27 -2 curves here. So now in higher rank, so here an example with 66. So for all of these cases, I can describe the intersection matrix, the dual graph of the -2 curves. So here you see the 240 -2 curve, and that example we spoke about. Rank 10, there is, so it is the bigger number. 240 is the bigger number of -2 curves. I know. So here 145, it is only a lower bound. I don't expect that there are more -2 curves, but I only have a proof of a lower one. Yeah, the rank, so the last here is rank larger or equal than 15. So it is 15, 16, 17, 18, 19, and there is no rank 20 K3 surfaces with finite automorphism. In fact, that was known, by example, by Shioda. Okay, so yeah, here is the classification. So you saw in these 2 slides the 118 families. So and the number of curves on these 118 families. So again, for each of these families, I can describe these -2 curves. And so when there is a U, it means unirational. So here, many U means the unirational and the higher rank come from the 95 famous K3s of Ride and Yonemura. So I would like to come back to the, oh, okay, I must stop soon. So I will skip that example, and maybe, is it okay for Yeah. I think 3 minutes, it's okay. So I will speak about the last example I wanted to show you. So the lattice U4 plus A1 to the cube. So it is a rank 5 lattice. It contains 24 minus 2 curves. And this is a double cover bunched over a smooth static curve. And the 24 minus 2 curves are pullback of 12 conics from the double cover. And these are irreducible components of the pullback of these 12 conics. And so they have a very nice configuration. I will try to show it to you. So you can partition that this 24 minus 2 curve into 3 sets, S1, S2, S3. So each set has order 8. And when you take 2 sets, S and S prime, so you give the color, so you can associate the following graph. So it's called a Levy graph. You put in red the curve in S, and you put in blue the curve in S prime, and there is, so that red curve cut the blue curve, that blue curve into the intersection number is 4, but that red curve and that red blue curve have no intersection number. And moreover, you can compute the intersection number, by example, between that red curve and that red curve. The intersection number will be 6 because they are opposite. And for the other red curve, the intersection number, by example, that red curve, the intersection number will be 2 between that one and that one. And the same for the blue curves. You can read every intersection number of this. So here you see only 16 minus 2 curves. For me, it's nice. Okay, and now you can, so here I gave a description as a double cover. Sorry, I'm coming back. I gave a description as a double cover, which is bunched over a smooth 60 curve with 12 conics, which are particular, but I don't know how to construct these 12 conics on the plane. However, if I can consider another model. If you take a Neff divisor of square, some Neff divisor of square 4, you can prove that there is a projective model of your surface as a quartic, which has a node. So it is a singular model which has a node at some point, and which has that equation where Q2 and Q.2 are quartics. And you can obtain that, so using that equation, you can obtain that the moduli space of these surfaces is rational. And you can see some of the minus 2 curves. So when you take the coordinate equal to 0, x equals 0, z equals 0, y, and t equals 0, that gives you various hyperplane sections, which are union of 2 conics. The 2 conics with equation, you see it. So that gives you minus 2 curves. But I didn't find where are the other minus 2 curves in that model. So thank you very much for listening.
Thank you, Xavier. Let's think.
Thank you.
Any questions? Okay. Question from Jihun. For a K3 surface with finite automorphism group in 95 families, does the automorphism groups come from automorphism group of the ambient weighted projective space?
I have no idea. Yeah.
So question basically is that automorphism group preserves this polarization.
Yeah, but you know the automorphism group is very small. It's like z over z2 or z over z2 to the square. So it might be, but this automorphism group is always very small. It was studied by Kondo, and maybe one can check that.
Another question: do they contain acyclic subgroups of non-symplectic automorphisms?
So, if I remember correctly, the paper of Kondo for generic K3 with finite automorphism groups, there is no non-symplectic automorphism. Well, that must be checked, but it is what I remember. So, yeah, it's trivial. There is no non-symplectic automorphism.
I have small question. In rank 7 and rank 8 case, you have 27 minus 2 curves, one case, and 56. Are these double covers of cubic and
Yeah, it's generalization of the del pezzo degree 1. Well, it is the family. You take a double cover, some particular double cover of degree k del pezzo, and you get these numbers: 27, 65, 66. Yeah.
Any other question? Okay, if there are no more questions, thanks Xavier again. I record the talk, and if Xavier is happy with it, I will upload it. Yeah, let's thank in the Zoom. Yeah, thank you, Xavier.
Thank you very much.
Very nice slide. Thank you. Okay.
Thank you.
See you.
Thank you.
Bye.